But I'm very excited to be here. Today I'll talk about statistical learning on period app data to advance personal healthcare for women. And I'll mainly focus on the methods that I'll present later. And I'll first have some common ground, have everyone agree with my introduction. Women menstruate, first fact of the day. So here I also talk about the biological gender, not the biological sex, not the gender. And why is that actually important for women's health? It's not just bleeding every other month. It's actually a crucial part of the reproductive system. And so it's a crucial part of our survival as a species. And for anything that's essential, then the biological pathways that regulate this have far-reaching effect beyond the reproductive system in general. And so it has impact on health, on emotional states, on our behaviors in ways that we're not necessarily even aware ourselves. The heart rates goes up and things like that in different phases of the cycle. And there are actually estrogen receptors virtually in every tissue of the human body. And so this makes this fundamental biological rhythm very essential to understand women's health and to improve some aspects from ranging from physical health to psychological health and things like that. However, it's as a field of research, it's an understudied, underfunded, and almost monodisciplinary field of research compared to other studies on biological rhythms, such as the circadian clock. There are still a lot of things that we really don't know about the menstrual cycle, and notably, we don't really know what are the causes of premenstrual syndrome and premenstrual dysphoric disorder. It is thought to be the cause of the increased suicide rates in women, but we don't really know why it happens. There are several hypotheses, and we'd be very excited to talk about it with you. Those are all topics I'm interested in. Also, as humans as a species, we are seasonal. We have a seasonal component in our birth, so that means there are more babies born in certain moment of the year, and it's not the same depending on where you live. And we don't really know what is the aspect of fertility that is seasonal. Another thing that we don't really know about the menstrual cycle is really how the menstrual bleeding is actually regulated. So it's a very human thing to be bleeding, to have menstrual bleeding. So a lot of species have an ovulatory cycle, but they don't have menstruations. So we don't really know very well how this happens. And this has consequences in the sense we don't really understand what are anovulatory cycles where there is no ovulation. And finally, we also don't really know what drives the irregularities and why some cycles are longer than others. And all of this has impact on the health, and actually cycle length is a good indicator of overall health in women. One reason why we may not have answers yet to those questions is maybe because of the lack of data. And so smartphones have helped a lot in that, because there are lots of menstrual apps that have been on the market, and millions of women are using those apps. Actually, it's one of the most health record tracked in all the health records you can think of. And these are examples of de-identified data that I obtained from 3 different collaborations from users that have been tracking for several years, almost every day. And this is very interesting. So these are 2 users. We have 2 time series, one on top and one at the bottom, and they tell very different story. The user on the top is very likely subfertile, has lots of anovulatory episodes and lots of heavy bleedings and things like that, while the person at the bottom has very regular cycles, goes through pregnancy, breastfeed, and then goes back to have regular cycles. And all of this, I can tell you, I can give you the context, and so I can just visually, because I know what kind of signal to look for, tell you, oh, those are cycles after the pregnancy, those are cycles before the pregnancy, and so on. And so putting these data into the context of the reproductive life of these users is very important to do any epidemiological studies on these data to try to answer the questions I was mentioning at the beginning. So that's the problem, actually. That's the main thing. How do we label these time series? And so this is where machine learning is very helpful. And so just to continue to introduce the framework that we want to use to label those time series, just a little bit of the comparison between how deep learning that everyone's talking about nowadays with human-like learning. So deep learning needs a ton of labeled data. In our case, we don't have any labeled data, right? We just have a big, massive data set of time series. But humans, they learn a bit differently. They have they have facts and contrasting information. So if we want to differentiate between dogs and cats, we can just say like, oh, all the things they have in common, and here are all the things they have different. And then we give just a few examples, right? And so statistical learning or model-based learning kind of is inspired more of the latter. So trying to just label a few time series. So this is something I can do in the evening when I'm not too tired, but is easy to do and is pretty cheap. And then I can use all the knowledge that we have about reproduction to infer that, like as a prior to the model. So what knowledge do we have? So we know most of the time cycles are ovulatory. So it starts with the menstruation in red in the middle. We go through the blue phase, the follicular phase, and then there is the ovulation and then the luteal phase. And then once in a while, there is an ovulatory cycle or a pregnancy. And then if we have a pregnancy, then we either go through birth or we have a pregnancy loss. If we have a loss, we go back to having ovulatory cycles or anovulatory cycles. And then if there is a birth, the person who gave birth can breastfeed or not breastfeed, and this will just change how quickly they return to having ovulatory cycles, right? So this is the broad knowledge that we have about how reproduction works. And we have a lot of information on how long these things last, right? We know menstruation is about 5 days, pregnancy is about 9 months, right? We have this information. And we also have observable variables that are significant, characteristic of these different states. So the bleeding or no bleeding, the temperature, the body temperature, the mucus, and things like that, or LH test. And all of these variables are actually what people log into the apps. And this is what we want to use. So what is the right framework to use this information and use it to label the time series? Well, most of the time when we have a graph with states, and observed variables, hidden Markov models are a good choice. But in this case, we want to use semi-Markov models. So I'm just going to quickly go through this. So hidden Markov models, we talk about different states that are hidden, and we can transition between those states. We also know what is the initial probability to observe one or the other states, and then the sequence of states. From the emission probabilities, we can see what are the observed variables, right? So the matrix, the gray matrix is what we observed. In a semi-Markov model, it's almost the same, except that we don't have the transitions to stay in the state, but we instead have a sojourn distribution that shows us exactly the time we spend in a state. And that's very useful because we can have any kind of distribution we want and not just the geometric distribution that's allowed from a hidden Markov model. And these semi-Markov models, they are used, for example, in annotating genetic sequences of DNA. So this is another framework where it's used. The thing is that most of the genetic sequences don't have that much missing data as we have in any digital health project. So we have a workflow that is based on interactive boosting. So we first design the architecture. So everything we know, we put it, right? So it's a bit like human-like learning, we put all the information there. And then we manual label a few time series. I work with R, so this can be done with a Shiny app. And then we can go through fitting the model, decoding, assessing the accuracy and the confidence we have in the model. And then we can manually go relabel what the model got wrong or validate what it got it right. And if we do a few times, at some point we'll be happy with this, and we can use this model to decode every other time series that we have. So, and the epidemiological studies we want to do. So some of the results, so here what is extremely encouraging in this work is to look at the histogram of the confidence score. So the confidence score, I'll talk a little bit more about it later, but it's basically, it's a non-parametric bootstrap approach that tells us at each of the time point whether we're confident or not in the decoding that was done. And it's completely independent of whether we have actual labeled data or not. So it could even work for completely unlabeled data. But in this case, we have a few labeled data. And so we can see that the confidence score is much higher when we got it right than when it got it wrong. So that means that somehow we can trust really this confidence score to assess whether we guessed it properly or not, even when we don't have ground truth. So just to give you examples, so this is one user, and the first lines above the gray line are the observations, and the four bottom lines are the decoding. The very last line are the manual labels, so the ground truth. And so you can see I was very lazy, so I only labeled like a small part of the time series. But then I can see what was decoded, which is the third line, so the one that's the longest with all the vertical bar, and so all the colors are the different states I presented below. And we can immediately see that there are some pieces that got wrong, but then most of it got right, and very likely everything that's besides the pregnancy was correct. It looks like it guessed it was ovulatory cycles, and I can see that. So I could validate all of these time series and have more labeled data. This is another example, and you see it's a similar story. So pretty encouraging. There are a few things that are wrong. So for example, we have some red here at the back. But honestly, looking at the data, it's a little difficult. There are lots of missing data. So my ground truth could also be not exactly accurate in this case. So it's always a balance between the two. So just to conclude this, so we have an upgraded, so it's all the work I did on this semi-Markov is based on an existing package, but it has been upgraded so that it can deal with a high level of missing data. So this is especially useful for any digital health project. It allows for any parametric or non-parametric distribution of the observed variable, and you can combine any kind of variables you want. So if you have discrete or categorical or continuous variables, you could combine like heart rate with any categories. And we can quantify uncertainty by providing this confidence score I was talking about that is based on a parametric bootstrap that is completely independent on whether the data are labeled or not. And all of this is available on my GitHub. It's still work in progress, but if you want to discuss it, I'd be very happy. And what is also great is that this model can work at different time scales. So we can label the whole time series over several years. But if we zoom and look in the day-to-day, we can see that ovulation day is actually predicted pretty accurately. And so with this, we can have all of our time series labeled and then integrate this data and see what are the difference before, after pregnancies and things like that. I want to thank my mentors at Stanford University and at Columbia, the companies, the apps I work with, and then the funding I received. Thank you.